All right, friends and neighbors, welcome back to the CCNA series. We are doing chapter 3, which is all about the fundamentals of WANs and IP routing. Now, as a reminder, right, there's the book that we're using, and I'm sort of going along, sort of expecting that you're reading along with me, so that's how I'm handling the chapters. I will be providing a lot of links in the show notes, and a lot of those go with these two books that I wrote for O'Reilly, right? So for additional materials, you can look for the chapters and the videos from those. Okay, well, let's get started. So in this video, we are going to cover some general WAN terms. We'll demonstrate some WAN examples. So I'll do that in Packet Tracer. And we'll also do, Ethernet as a WAN technology. And then we'll jump to some layer 3 stuff with routing. And so we'll do a router encapsulation example, another topology, and we'll show you how that works. And then the sort of trifecta, IP routing and IP packets and a little bit on IP addressing. And then we'll close this up with a discussion about DNS, ICMP, and ARP. And these are some of the tools that we can use, some of the basic protocols that we have in networking. We use them all the time. But of course, what we're going to do first is, did I know this already set of questions. Now, as we get started here, I have to admit, I got tricked by the wording on some of these questions. It's also interesting that some of these terms are a little dated. They're still on the CCNA exam, so that's why the chapter is covering them. But man, I was like, wait a minute, what are we trying to ask about here? Okay, so the first one, which of the following terms is not commonly used to describe a serial link? Well, there's a bunch of terms, but the one that doesn't really fit is E-line. And that was actually the first place I went, wait, what? Because there is a thing called an E1, but not normally used for, how we talk about a serial link. Now, I'll talk more about what it means to be serial here in a second. Now, this is the one that really got me. Two routers, R1 and R2, connect using Ethernet WAN service. The service provides point-to-point service between these two routers only as a layer 2 Ethernet service. Which of the following are most likely true about this WAN? Choose two answers. Well, B and D were the right answers, but I had to puzzle over this one for quite some time just because of the wording. But B and D say R1 will connect to a physical Ethernet link, and the other end of the cable will be to a device at the WAN service provider, point of presence. Now, the assumption here, I think that the question is making, is that there's a couple of sites that are connecting to the WAN provider, and the routers are not actually connecting directly to each other. And then D was router 1 will forward data link frames to R2 using an Ethernet header or trailer. And I'll actually show you that topology here in just a few minutes. Imagine a network in which PC1 connects to the same Ethernet LAN as router 1. PC2 connects to the same LAN as router 2, and the two routers connect to each other with a PPP serial link. Now, the thing that we had to know is what in the world PPP is for. Well, PPP is the point-to-point protocol. Hasn't been used in a little while. The last time I used it was with dial-up networking. And PC1 sends data to PC2. Router 1 removes the Ethernet header and trailer. Which of the following is true? Well, the answer to this one is that router 1 does not use the removed Ethernet header or trailer again. And we will see that routers destroy layer 2 frames and then move on. Okay, so by the way, I thought I would do these questions as a way to help you through this and why the answers are what they are. But if this gets a little dull or it's not as interesting, go ahead and tell me in the comments, and we can skip this part for future chapters. Okay, which of the following does a router normally use when making decisions about routing TCP packets? That one's actually pretty straightforward. We have to process things at layer 3, so that is going to be the destination IP address. We don't worry about the source because we're trying to get to the destination. Which of the following is true about a LAN-connected TCP IP host and its IP routing forwarding choices? Well, so the answer here is C, and what that means is that the host actually has the ability to determine whether or not the destination is on its network or not on its network. And so if the destination is off of the network, that's when it sends it to the default gateway. I'll show you that too. Question number 6, which of the following are functions of a routing protocol Well, the whole idea, whoops, let's do this. Hopefully I didn't skip one there. No, I think we're good. Okay, in a routing protocol, that's A and C, which means that routing protocols advertise known routes to neighboring routers, and let me see, learning routes as advertised to the router by neighboring routers. In a routing protocol, the whole point is to tell your neighboring routers about what you know, and you learn what they know. So that's why it's A and C. A company implements a TCP/IP network with a PC sitting on an Ethernet LAN. Which of the following protocols and features require PC1 to learn information from another server device? That was the keyword and tricky phrase. All of these are part of a network, but the server that we need answers from is from DNS. Okay, that'll about do it there. Well, on to wide area networks. So, the easy way to think about this is that you've got your internal networks. You got to connect to the rest of the world. So that connection is to the WAN or the service provider, your ISP. Now, there's lots and lots of ways to connect to your service provider, but we just say WAN link or WAN connection. But WAN links are really about layer 1 and layer 2. Now, there are a lot of times routers on either end, but the actual connection is really about layer 1 and layer 2. So to start with, right, the book talks about two kinds that we have. Ethernet WANs and then leased line WANs. And this is the thing that's a bit old but still part of CCNA. So we'll take a look at some of the ideas there. But today, of course, we also talk about cable and fiber and even DSL technologies. But the thing that you have to remember is that if you're talking straight fiber or DSL or cable, DSL is over twisted pair like telephone wire, that's just layer 1. We have to remember that no matter what we're talking about, we have a layer 2 encapsulation that has to happen. And so I will show you a topology here. We'll actually put some modules in a router or switch, and we'll see how that goes. Well, let's get some terms out of the way. These are all things that you find in a discussion about WANs, right? So we say that we're leased circuits or just circuit, right? That's the electrical connection. So if you think about an electrical circuit, it's not much different. We are establishing a circuit between two endpoints. Now the fun thing about this is that it's serial. And what that means is the bits flow or are transmitted one by one. When I take a look at my Ethernet cable, right, this thing here, there aren't very many wires in here. 2 are used for transmit and 2 are used for receive, as we talked about when we got to Ethernet. More advanced forms of transmission exist, but there's only 8 wires in here. So we transmit the bits, one at a time, 10, 10, 10, 10, like that. Now, historically, that hasn't always been true. Here is an example of, a zip drive, right? This is a zip drive. And so if you look there, hopefully you can all see this. These are parallel ports or parallel connections, and these have a lot more pins. Now, some of those pins might be for different reasons, timing or something of that sort, but a lot of them are for data transmission. So you're transmitting a whole bunch of data lines at the same time. But this is big, right? It's a big port. It's expensive, a lot of lines, a lot of wires. It turns out that in order to increase speed, it's more efficient, it's better to see if you can make one set of lines or a couple of lines go really, really fast and dedicate resources to that rather than trying to build bigger and better pathways. So we don't do that very much on machines or network connections these days. However, we do still use parallel lines inside a computer. So your computer bus is a whole bunch of data lines going on at the same time. But that's one of the last places that we actually see it. Point-to-point link or line is just, it's really what it says. So in the diagram below me or off to the side, right, is R1 or R2 and R3. Those are connected via point-to-point. That means that they're connected directly to each other. There are no hosts in between them. It's just one line between them, and that line can be full duplex. Another term that we see used, it's a very traditional term, we don't see a lot of them anymore, is T1s. Now a T1 is a telco transmission standard. It is 1.544 megabits per second, and a very common configuration is to have 24 DS0 channels or circuits. Each is 64 kilobits per second. And the encoding that we use for our voice is G.711. So those all sort of go together. It's a very traditional thing. A company would lease a T1 line and, spend a couple $100 every month on that level of connectivity. A very general or generic term is WAN. So if somebody just says WAN link or WAN or just link, right? It's a very generic term. There's a lot more detail that could be provided there, like what kind of WAN link. We sometimes say private, and this goes back to one of the do you already know this things. It's also sometimes called private, which simply means that if you're at a point-to-point link, nobody else is sharing that connection, so nobody else can see your data. Okay, so let's take a look at Packet Tracer here, and we'll take a look at what we can do with some of these modules. So here is the topology that I wanted to use for this particular demonstration, right? And maybe what I'll do is undo what I did, or maybe I'll just delete this device. And so you can see that we're going to just delete these, right? And we're going to add a couple of routers here. So I'm going to stick these routers right back in here. Now, if we're used to standard routers, we can see that I've got a couple of Ethernet ports here. And when I do my configuration, right, there they are, okay. We'll be patient, right? Right there's my fast Ethernet 0 and fast Ethernet 1. Not a very fast machine, but there you have it. But if we look at the physical chassis, we have all of these slots here. So if we were not talking about Ethernet, what would we be talking about? We might be talking about serial interfaces. Now we take a look at the side here. These are a whole bunch of modules that we might install in this particular router. Now I'm going to install one in each one, and I'm going to do the same. So I'm going to select a WIC 2T. Now I'm going to get a warning here. It's going to say, hold on a second. You cannot do this when the router is powered on. So I'm just going to turn it off. Now this is what we call the difference between hot swappable and not hot swappable. So now that the router's off, I'm going to go ahead and do that, and then we'll turn it back on. So now this router is booting, and I'm going to do the same thing over here. So we'll turn the router off, and I did a 2T module right there. So we'll put this one over here and turn the router back on. Now, if I look at my connection types, I can see, I can see down here, I've got these sort of red squiggly lines. If you can't see the red too well, they're just squiggly lines. And it says serial DCE or serial DTE underneath them. And so what I'm going to do is we'll first connect the Ethernet, right? So we'll take an Ethernet connection and we'll run it to the fast Ethernet. But we can see also that I have serial links as well. So let's finish our Ethernet. And I've got a couple of ways I can turn this on. We'll do the quick, simple, and easy method, right? I'm going to turn on my fast Ethernet on that side. And we'll turn on my fast Ethernet on this side. But there's the serial links. So now if I take a serial cable and it says, well, where do you want to connect this to? If I try to connect it to fast Ethernet, it says, oh, no, you don't. So I need to connect this to a serial link. And this right here would be an example of a leased line connection or a WAN link that I would connect to my service provider. Now, I didn't put a router out here in my cloud, so I'm just going to run it straight across here to another serial interface. And of course, I would do a full configuration and all of this, but for right now, I'm just going to turn them on. There we go. And the serial links are coming up. So that is what we mean by this. Now, these are not Ethernet links. They are serial links of some other kind. Now, we still need a layer 2 encapsulation of some kind. We're getting very used to the idea that I've got Ethernet frames flowing across my Ethernet network, but that's not what this is. This is something else. So the question is, what might it be? Now, even if it was cable or DSL or fiber, it probably is not straight up Ethernet, or Ethernet as we've come to know and love it. It might be, but we have to understand that there might be different encapsulations out there. So before we dive into what might be going over that link, let's remember our Ethernet frames. So in an Ethernet frame, right, we have the preamble, the destination, and the source MAC addresses. We have a type, and then we have our data that we're carrying, and then some kind of error control here. So we have to build a frame that is all about this error control and getting addresses and figuring out what we're carrying, that is the type. So those are the main things that we think about when we're trying to build an Ethernet frame. And remember that some of these fields are visible when we look at an Ethernet frame in Wireshark, but we can't see it all, right? We can't see the preamble of the frame check sequence, but we can see the MAC addresses and the type. Okay, so that is an Ethernet frame, or what we might say Ethernet encapsulation. Well, if it's not Ethernet, what might it be? So the chapter talks about two other serial framing or encapsulation types. That is the high-level data link control, or HDLC, and the point-to-point protocol, or PPP. Both are a little dated, right? They're not really used very much, but you can specify if you had serial connections in your router or going off-site, you might actually specify the encapsulation. So when we build serial links, you absolutely can specify those encapsulation or what you want to use, depending on what's on the other side. Now they're probably going to be a little bit slower than, gig Ethernet, but there we have it. Now, of course, there's a standard that goes along with this. So HDLC comes from the International Standards Organization. There's the standard there. It is the OG. It's the original data link control encapsulation that we use. And it came from IBM's SDLC, or Synchronous Data Link Control Protocol. So you might say that's actually the OG. But the standard that we build everything on is HDLC. PPP was often used for dial-up and PPTP VPNs, point-to-point tunneling protocol from Microsoft. So all the way on the side here, we've got what HDLC looks like, and this is right from the Cisco Learning Network, and you can see that if you have two Cisco devices, you could say, I want to use HDLC encapsulation. And here's an example of an actual PPP capture, and you can see that it's got an address here, and then control of some kind, and then what am I carrying? The thing that you can't see is the preamble and the frame check sequence. But it's the same idea. There is one difference, though. On a point-to-point link, I often don't care about all of the other addresses. I just want to know who I'm sending this to. So sometimes we can get away with one address. So encapsulation and de-encapsulation. So here's a couple of ideas that we need to realize. MAC addresses and frames do not survive past a router. We use frames to communicate with anybody that's on our network, including our default gateway. Routers destroy frames and build new ones as they forward things out the other side. So frames are used only at layer 2, and we usually never learn the MAC addresses of anybody that's not on our network. And let's not forget about our routing tables. As we're forwarding traffic, the minute it goes to a router, the router is going to use its routing table to decide how things are going to be forwarded. But a host also has a routing table that it can use to help figure out how things are going to go. Well, let's see an example of this encapsulation and de-encapsulation. So we are back in Packet Tracer. I have a different topology for you here. This one is entirely Ethernet, but all that we want to do is see the encapsulation and de-encapsulation. So what I've done in this case is I've said, okay, I've set up a host over here, 192.168.1.0. It has a router that it's connected to, the default gateway, 1.254. That router has a second IP address of 2.254, and then over here we have another host. So we want to verify that we have connectivity. So from 192.168.1.1, I'm just going to try to ping my gateway, and we'll see if that works. It looks like it works. And then we'll go for broke. We will try to go all the way to the other host. We'll see how this works here in a second. Hopefully I set everything up. There we go. All right. Now, I'm using ping. We're going to talk about ping in a little bit here. But what I really care about is the encapsulation and de-encapsulation. So now I'm going to start our simulation, and we'll cut out some of the stuff here that we don't want. There we go. And I am going to do the exact same ping again, but we're going to watch what happens at layer 2. Now, I have included the MAC addresses here. So what the chapter talks about, and what I'm going to show you right now, is that the packet is going to go from 1.1 to 2.1. But the MAC addresses are going to be from PC2 on this side, this MAC address right here, to the gateway. The gateway is going to destroy the Ethernet frame, take the IP packet and put it inside a new Ethernet frame that goes between this MAC address on the other side of the router and the destination. So that's a really important idea. So the router is going to destroy the frame on one side and build a new one as it goes. So here we go with our ping. And we can see it go. So let's take a look at this one right here. And we will take a look at the MAC addresses at layer 2, which makes sense because that's where MAC addresses are. So the destination is right here. Right? Now hopefully you can see this, but it's 0801 in the last 2 octets. That is the MAC address of the router. And where did this come from? It came from 0B92, which is the MAC address of the 192.168.1.1 node. Okay, well let's keep going and see what happens on the other side of the router. There it goes. All right, so we'll pause it. So the frame that was on its way to PC3 from the router via the switch, where did it come from? Well, the destination was 3646, which is the MAC address that you see right here for the PC. Where did this come from? 0802, which is the interface right here. So, the important detail is that, we'll go back to real time here, the important detail is that the router and the PC on one side built a frame, it got to the router, it was destroyed by the router built a new frame to forward it out the new interface. And then the process would be the same, but in reverse, going back the other way. That is the idea of encapsulation, or what happens on one side of a router versus the other. Okay, so Ethernet WANs today, could we use a LAN protocol? Well, so the real question here is that instead of all that serial line, leased line, HDLC, PPP business, could I have just run Ethernet from one site to another? Could I have run Ethernet from my router out to my ISP's router? And the answer is absolutely yes. Fiber and standards such as the 1000 base whatever standards allow us to reach more than 10 kilometers. This makes Ethernet viable for many applications. And let's not forget that we can get higher and higher speeds. So let's take a look at 2 things real quick. First, we'll take a look at the standard. So this is the 802.3 2012 standard. And here is a collection of the speeds or the versions of Ethernet that are included in this particular standard, and this is just in section 5. So we can see the data rates here, 1000 megabits per second, 1000 megabits per second, 10 gigabit, right? This is 1 gigabit, 10 gigabit, 10 gigabit, 10 gigabit. So these are in the earlier standard, right? Take a look at these, the nominal reach, the normal reach for these. And here's one out at 20 kilometers, 20 kilometers, 10 kilometers, 20, 10. So it's very easy to see that Ethernet could very much reach as far as we need it to. It would be strange if your ISP was maybe farther than that, or you were just going in between buildings on your campus that you would need to go farther than that. But there are standards that allow us to do that, or repeaters that allow us to do that. Let's also go back to our serial connection in our in Packet Tracer and take a look at what other modules we might use. So if we go back to this topology again, we know that in this router, I put in here these serial boxes. That tiny little interface right there. I don't know if you can see that. Whoops. Oh, there we go. Zoom in. Okay, so this interface right here is a serial interface. But what if I picked something else? What if I did something like this? All right. Okay. Sorry. I don't know which one I grabbed, but there we go. If I take a look at this hole right here, this square peg right here is for another small form factor module to go in there. And you can see that it says gigabit Ethernet right there, and that's an SFP module. I could put a fiber GBIC in there or another UTP, which would be gigabit, which I could run off-site, especially if it was fiber. Now, hopefully I'm not covering up too much of this slide with my noggin here, but let's talk a little routing. So we're going to move away from layers 1 and 2, so I'm not going to care too much about those lower layer thingies. I don't really care about whether or not you're doing fiber or cable or Ethernet. I don't care as much about what the frame is carrying. Instead, we want to put IP packets out onto the network and then get them to their destination. And the minute we say we want to do that, we're talking about routing. So the big idea here is that routers route packets, but hosts have their own routing table. So the router's whole job is to route, right? Take IP packets from one place and get them to another. In other words, they forward. But a host starts the process by deciding whether or not it's going to forward something to a router anyway. So here's another idea. Routers don't know all the answers, so they can ask other routers for help. Just like a host has a default gateway, a router can have a default gateway. A router can also be told, listen, if you want to get to this network, go that way. So you could configure a router to do that. Or routers can run a routing protocol to help them figure it out automatically. Now it's all about the tables. So we've got router routing tables, we've got host routing tables, and along the way, as we're forwarding packets, everything does the frame check sequence. Let me say that again. Everything does that touches the frame does the frame check sequence. If you are touching the packet, then you're also going to do the IP header checksum. So there's lots of error checks along the way. Let's take a look at some examples. So what I'm going to do is I'm going to add a router to my topology here. So hopefully this doesn't take too awful long, right? It's not bad video, but here we go. And we'll put a host out there as well. Now I'm going to use the CLI. We're going to use the CLI next week as we go through some examples. That's what chapter 4 is all about. But here will be a quick example of how to work with the CLI. I'm going to go into interface F0/0. Now, there's an idea that we're going to talk about later on in this video, and that is address space, right? Here is one network here. So when we say networks, I might say this is the 192.168.1.0 network, and this is the 192.168.2.0 network. Whoops. And over here will be the 192.168.3.0 network. So those are the networks that I'm trying to get to. And when I configure things, everybody that's connected to a particular network has to get their IP address from the same address space. So I'm going to say IP address for this guy, 192.168. Now I can't reuse them, so I'm going to make this 253. Now, if you're wondering what in the world I'm doing, do not panic. We're going to do many of these. And I'll include links in the show notes to piles of videos where I've done this stuff. And then I'm also going to turn the interfaces on. Okay. And then we'll go to the other interface and we will give it its IP address. That'll be 3.253 over there. And we'll say no shut, which is Cisco speak for turn it on, please. Now in the host configuration, I'm going to tell the host that its default gateway will be 192.168.3.253, and then its IP address will be 192.168.3.1. There we go. Okay, so these are coming up. Now, while I'm at this, Packet Tracer is a simulation, so it doesn't show you everything, but I want to show you something. We'll see if we can get Packet Tracer to show it to us. If not, I'll show you on my own machine here. Okay. So this is part of the host routing table. And we can see that my host routing table has a default gateway of 1.254, and that I get there by using this particular interface. Now, just for fun, here is a much larger host routing table, an actual host routing table from my machine here. So this is my IPv4 routing table. Now we'll learn how to process this later on, but you can see that the host has a lot of decisions that it can make long before it ever decides to send something to a default gateway. So what we want to remember for right now is that when we try to forward packets along the way, what starts the process is the host handling its host routing table. Then when we get up to the router, we say, well, what does your routing table look like? And this is a router routing table. This router right now knows about the 1 network and the 2 network. Now again, if this is a mystery to you, do not panic. We're going to do lots of these. The book doesn't actually go through this example. It talks about how routing works, but I wanted to get a routing topology set up so that we could talk through it and cover most of what the chapter talks about. What is missing from this routing table, of course, is that there's no mention of the 3net here. Okay? So that's what we have to tell router number 4 about. Now, what does router number 8 know? Well, as you might guess, it is situated between the 2 and the 3net, so it understands that it is connected to the 2 and the 3net. What is conspicuously absent is the 1 network, which means that if I tried to go from this host all the way over to here, it would fail. And let's put a label on that host just so we know. All right, this is 192.168.3.1 over here. Now you don't have to believe me. Let's try this just for fun. So I'm going to ping 192.168.3.1. And it says destination unreachable. Okay, so it can't get there. Well, the obvious problem is that the 2 routers don't know how to get to the other destination networks. Now, I'm going to quickly solve this today, but later on we will go through this, and again, lots of links in the show notes if you want to dive deep before we get there. So what I'm going to do is I'm going to tell this router how to get to the 3net. I'm going to include something called the network mask and the next hop to get there. So what did I just do? With that command, I told the router how to get to the 3 network. There it is right there. But I haven't solved the problem entirely because this router here, router 8 in this case, does not know how to get back to the OneNet. So let's solve that problem too. So I'm going to tell it how to get to the OneNet, and this will be via the router on the left, or at least that router's IP address. So now if we take a look at the router routing table, there we have it. The one network is now in place. Okay, well, let's give this a whirl. So our last thing that we tried was 3.1. Now this might take a second because everybody's trying to figure out everybody's MAC addresses. There it goes, success, huzzah. So it works. So how did this happen? How does this work? Well, we'll do a simulation and maybe we'll watch it go. But the thing that we want to realize is that the PC all the way on the left says, I'm going to look at my host routing table and I'm going to find out that the destination is not on my network. I'm going to send it up to my default gateway. It's going to look at its routing table, figure out that it knows how to get to the OneNet because it's via router 8. Router 8 gets this packet, says, where are you going? Oh, you're going to the 3net. I'm directly connected to that. I can send it on. Host over here on the right says, oh, who is trying to talk to me? That's somebody all the way here on the OneNet, not on my network, and I have to send it back to my default gateway, and so on. So we'll watch this go, and we'll step through it. So there it goes, right? Host routing table was processed. It gets out to the switch. Switch processed its source routing table, sorry, source address table. The router is now processing its router routing table, says I know how to get to the 3net. Forwards it across to router 8. Router 8 says, where are you going? I know where that destination is. Gets all the way to the host. The host has to respond now. It says, what's in my host routing table? Oh, I need my default gateway. Sends it right back, in this case, to 3.253. Remember, we're doing all that encapsulation now. So now we've got 3 Ethernet frames that are destroyed and then rebuilt. The OneNet is available via router 4 and then on to the destination. And there we have it. Now, an important thing to realize is that what were we processing just at that point? Well, we were processing IP packets. So the routers were looking at the destination here in the IP packet and trying to say, all right, where are you going? Do I understand where that network is? Now, along the way, we might be doing a lot of processing, right? We've got this header checksum that might be processed. There might be quality of service settings. But at a minimum, we are going to handle the destination address and determine how to best forward this particular IP packet. We are going to spend a lot of time on these later on. So IP addresses, networks, subnets, and internetworks, oh my. Okay, so when we say network, it has a very special connotation. The hosts inside a network share the same address space, and the space is defined by the network mask. Whatever network mask you have, that tells us or specifies what your address space is going to be. So nodes inside a network or inside a subnetwork have meaning together. They share that same address space. They can all reach each other with frames. When they process their host routing table, they find out that they're on the same network. And they usually all use the same default gateway when they need to go off of the network. So remember our post office example. We've got all of this forwarding going on. And the way we determine our forwarding is by the source and destination IP addresses, the source and destination MAC addresses, not unlike the addressing on a letter. And the routers act like that central office out there to forward packets. So if we go back to our example, and I've got this entire network right here, right? Everybody on this side of the router, they are going to share the same address space. They're on the same network. So this might be 1.2 and 1.3 and 1.254. Nobody else is allowed to use that address space. That means that they could talk to each other directly. They could build frames to each other directly. And if any one of them needs to get off the network, they would all use this router to get out, their same default gateway. Now, there are a couple of other things that were touched on in the chapter. The domain name system. This is a critical part of our infrastructure. Everybody uses it. In fact, almost every single internet transmission that you initiate uses the domain name system. Its main use is to resolve host names to IP addresses. So we're going to do an example here, and the tool we're going to use is NSLOOKUP, just like the one seen here. So what ends up happening is you say, I have a query. Can you tell me the IP address that goes with this host? And that is the normal way that goes on. And so we've built IP packets with IP addresses, but in order to do that, we need to find what the IP address is that goes along with the host, because we're humans. We don't talk IP addresses. Now, you can also do the reverse. You can say, well, I have this IP address. What's the host that goes along with it? Now, just like routers, DNS servers can help each other out, right? When one server doesn't know the answer, it can pass it along to another server until we eventually find somebody that has the answer. The whole system is built up of all of these databases containing resource records. The communication is an actual protocol that we use, and a resolver is the thing on every single host that asks the question. And we do messaging back and forth to get the queries out and then the answers back. So let's do a couple of examples. So I'm just going to run a program called NSLOOKUP. You can actually do this on your own machine. And my name server that I'm going to be using is 8.8.8.8 or Google. And I'll just look up www.rit.edu. There we go. So the answers that came back for me were the IPv4 and IPv6 addresses for rit.edu. So that is what we call a forward lookup. Well, what happens if I do the reverse? If I say, what is 129.121.40? Well, it turns out that is the web server called rit.edu. So this is a very, extraordinarily common. It's everywhere. We do this nonstop to resolve names and addresses so that we can browse to web pages, or so that we can open up resources so you can find your printers. We do this all the time. Now, the chapter touches on two other things, ARP and ICMP. The basic problem that ARP answers is that, well, we need to build an Ethernet frame. When I want to talk to anybody on my network or off my network, I need to be able to build an Ethernet frame for somebody. And the basic question is, how do I find out the MAC address of the destination so that I can build the frame? And the answer is the address resolution protocol, which is standardized in RFC 826. So you can go out and read about it, right? Like all of these things. But that's its job. Hey, everybody, who's got the MAC address that goes with this IP address? Somebody answers, and then you can build a frame. Now, as you saw in the examples earlier, I used ping to establish connectivity between the two sides. Well, what is ping? Ping is just a program. It generates ICMP echo requests. So an ICMP echo request is a special message that goes to the destination, and the destination says, I will answer you using my responder function, and I'm going to generate an ICMP echo reply. So this is a pretty standard thing about what we do. We use it all the time. It's a really basic troubleshooting tool, but it's very nice to know that ping is just a program that generates messages of a completely different type, ICMP. ICMP is the Internet Control Message Protocol. Now, it's much more than just echo request and echo reply. It is a collection of error and informational messages that help us solve problems or provide feedback. And yes, there's an RFC that goes along with that too. All right, the chapter 4 look ahead. Next week, we are going to be doing the command line interface. This was also the question that I had for you if you thought it'd be worthwhile to do a live demo. So if you think that that's maybe beneficial, let me know. Maybe we can set something up. But some of the items will be not just learning to use the command line interface, but configuring a terminal emulator, the thing that allows us to interact, some commands, and then we'll work with files, right? The files that will be on the devices that are used to control the device. Well, okay, that was WANs and IP routing. I decided to do it all in one go. So a WAN has a very historical sort of connection types. We think about serial connections, lots and lots of different kinds. But of course, today we talk about Ethernet WANs in a very similar context. And Ethernet certainly is considered a local area network protocol, but we use it out in the WANs all the time, mostly because of the distance that fiber can span. Of course, we talked about IP routing, networks and IP addresses, DNS, ICMP, and ARP, all part of networks, all part of operations that we do every single time we touch a machine and every single time we try to do something out on the web. Well, thanks for watching. Thanks for listening. Like and subscribe if I help, and may those WAN packets and routed packets always reach their destinations. And remember that we're doing this CCNA together. You can do this.